This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 4 of Week 4, Pump and System Curves. One of the highest yield ideas in the fluids section. A pump can deliver a whole family of head and flow combinations. That's its curve. A piping system demands a whole family too. That's its curve. Where they cross is the one point the pump is forced to run at, the operating point. We'll build both curves, read the intersection off an example, then watch throttling, valves, and elevations slide that point around. The single most important idea in pump analysis, the operating point, where two curves intersect. The pump curve is what the pump can deliver. Head falls as flow rises, so it slopes down. The system curve is what the piping demands. Required head climbs with flow, because friction grows with the square of flow. A pump doesn't pick its own flow rate. It's forced to run where the head it can make exactly equals the head the system needs. Find that intersection, and the whole problem falls out. Flow, head, and with the efficiency curve, power. Think supply and demand, clearing at one point. The pump curve. The manufacturer publishes head versus flow at a fixed impeller diameter and speed. 3 landmarks: shutoff head, the maximum head at zero flow; the best efficiency point, or BEP, where efficiency peaks, the design target; and runout, the maximum flow at zero head. Between them, the curve slopes steadily down. More flow, less head. Running far from the BEP invites vibration and cavitation, so a good selection lands near it. Lock this in. The pump curve belongs to the machine. Throttling a valve doesn't move it. Only changing the pump itself does. The system curve, the total head the piping demands to push a given flow. It splits into a constant part and a flow-dependent part. The constant part is the static head, the elevation lift plus any reservoir pressure difference. The flow-dependent part is friction plus minor losses, both scaling with flow squared. Bundle every loss coefficient into one constant K, and the system curve is H static plus KQ squared. At zero flow, there's no friction, so it starts at the static lift, its y-intercept. As flow grows, the KQ squared term takes over, an upward opening parabola. The variable table. Flow rate Q in GPM, the x-axis of both curves. Pump head, what the pump delivers. System head, what the piping demands. Static head, the flow-independent elevation lift. The system resistance K, rolling up friction and minor losses. And the prize, the operating flow and operating head, where the two curves cross. 1 unit caution, K carries feet per gallon per minute squared, so that KQ squared comes out in feet. Overlay the two curves on the same axes. Look at the figure. Plot the pump curve sloping down. Plot the system curve, the parabola rising from the static lift. Read the intersection. Drop down to the flow axis for the operating flow, across to the head axis for the operating head. There, the head the pump can make equals the head the system needs. And it's stable. Left of the crossing, the pump overpowers the system and flow speeds up. Right of it, the system outdemands the pump and flow falls back. Worked problem. A pump feeds a system that lifts water 40 feet. With resistance K of 6.4 times 10 to the minus 4. The pump curve is 3 points. At zero flow, 120 feet. At 200 GPM, 96 feet. At 300, 72 feet. Find the operating flow and head. The plan: build the system curve, 40 plus KQ squared. Tabulate it at the same flows as the pump data. The operating point is where pump head equals system head. Evaluate the system head at each flow against the pump head. At zero flow, pump 120 versus system 40. Pump wins. At 200, pump 96 versus system about 66. Pump still wins. At 300, pump 72 versus system about 98. Now the system wins. So the curves cross between 200 and 300. Interpolate to about 270 GPM and 87 feet. It's stable. Below that, flow climbs. Above it, flow falls back. On a graphical problem, you just read this crossing off the chart. Now the payoff. What happens when the system changes? Start with throttling a valve. A valve is part of the system, so the pump curve stays put, and only the system curve moves. Throttle or partly close the valve, and K rises. The parabola steepens, and the operating point slides left along the fixed pump curve to lower flow and higher head. Open it, and K drops. The parabola flattens, and the point slides right. Throttling cuts flow without touching the pump, but it's wasteful. The extra head is burned across the valve. Picture it as pivoting the system curve about its fixed y-intercept. The static head doesn't change, only the slope. The other system change is elevation. Raising or lowering the destination reservoir changes the static head, the y-intercept. Raise the lift, and the whole parabola shifts up by delta z. Slope unchanged. The operating point moves to lower flow because the pump has less head left after fighting gravity. Lower the lift, and it drops, moving to higher flow. Unlike throttling, this is a pure vertical translation. The curve keeps its shape. Keep the two motions separate. Throttling changes the slope and pivots about the intercept. Elevation changes the intercept and translates vertically. 4 traps. 1. Moving the pump curve when a valve changes. A valve is part of the system, so throttling shifts only the system curve. Only the affinity laws move the pump curve. 2. Confusing throttling with elevation. Throttling changes the slope and pivots about the intercept. Elevation changes the intercept and shifts vertically. 3. Forgetting the static head. The system curve starts at the static head, not the origin. A curve through 0, 0 is friction only, wrong whenever there's a lift. 4. Misreading the chart scale. Check axis labels and units before reading coordinates. Bookmark 2 pages. The pump curve characteristics and head loss for the system curve. The pump curve is head versus flow, sloping down, with shutoff, DEP, and runout landmarks. The system curve is H static plus KQ squared. Intercept the static lift, slope the friction. The operating point is where pump head equals system head. 2 shift rules. Throttle a valve to raise K, and the point slides left. Raise the elevation to raise the static head, and it also slides left. On a graphical problem, the chart is given. Your job is reading the intersection and reasoning about how it shifts. You now own the operating point, the intersection of a fixed pump curve and a movable system curve, plus how throttling and elevation slide it around. In Topic 5, we add a second pump and build combined curves. In series, heads add at the same flow. In parallel, flows add at the same head. Then we intersect that combined curve with this same system curve. The system curve doesn't change. Only the pump side does. See you in Topic 5.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.